You know, we think of flying as totally routine, just a way to get from point A to point B. But the moment you step into that airplane, your body enters an environment it was absolutely never designed for. So today, we're going to pull back the curtain on the hidden physiological challenges of aviation and what's really happening to you at 30,000 feet. And believe me, it's way more than just your ears popping or getting a bit of jet lag. From the very air you breathe to the way your eyes see, your body is under this constant invisible stress. So the big question is, what is actually going on up there? To really get a handle on this, we're going to break it down into 5 key areas. First up, we'll cover the fundamental rules of thin air. Then we'll dive into how those rules create the breathing challenge. After that, we'll look at the surprising dangers of pressure, bubbles, and bends. We'll also explore what's actually in the air up there with ozone and other irritants. And finally, we'll see why seeing at 30,000 feet is one of the biggest challenges of them all. All right, so to understand what's happening to our bodies, we first have to get a grip on the basic laws of physics that are running the whole show. And it all, and I mean all of it, starts with pressure. The first big idea we need to wrap our heads around is something called Dalton's law. Now, it sounds complicated, but it's not. All it means is that the air we breathe isn't just one thing. It's like a cocktail of different gases, and the total pressure you feel is just the sum of all the individual pressures from each gas in that mix. Look at this diagram here. Imagine you've got 2 different gases, each in its own container, pushing outwards with its own pressure. Well, if you mix them together in one container, the new total pressure is simply those 2 original pressures added together. That's it. Each gas is doing its part to contribute to the whole. And that's exactly what's going on with the air we're all breathing right this second. It's a mix, mostly nitrogen, a good chunk of oxygen, and then some argon and other bits and pieces. Each of those gases adds its own little bit of pressure, and when you add it all up at sea level, you get about 14.7 pounds on every square inch of you. Okay, rule number 2 is Boyle's law, and this one is huge for aviation. It's a simple relationship. As the pressure around a gas goes down, the gas itself expands and takes up more space. And if you crank up the pressure, you squeeze the gas into a smaller volume. Just remember that relationship. It's going to have some massive consequences for the gases trapped inside our own bodies. All right, so with those 2 fundamental laws in our back pocket, let's talk about the most basic thing we do to stay alive: breathing. You'd think it's simple, right? Well, at 30,000 feet, that simple act gets surprisingly complicated. Get this. By the time you climb to just 18,000 feet, the air pressure around you is literally cut in half. Now, the percentage of oxygen in the air is still the same, about 21%. But because the pressure is so low, the molecules are spread way, way out. It's like trying to get a drink from a straw that's full of holes. You can take a big breath, but you're just not getting enough oxygen. This whole situation leads to 2 major problems that, to make things worse, have really similar symptoms. First, you've got hypoxia, which is a genuine, straightforward shortage of oxygen in your body. But then you have hyperventilation, which is when you start breathing too fast and blow off too much carbon dioxide, usually because you're panicking about not getting enough air. And here is the really dangerous trap. When your body starts to feel the effects of low oxygen, hypoxia, what's your first instinct? To breathe faster and deeper, right? But doing that can push you right into hyperventilation, which, get this, doesn't even solve the oxygen problem and creates a whole new mess for your body to deal with. It's a nasty, vicious cycle. Now, it's not just about the lack of pressure. Sometimes the air you're breathing can become the threat itself. In a lot of piston aircraft, the cabin heater works by taking cold outside air and passing it over the hot engine exhaust to warm it up. But if there is even a tiny crack in that system, deadly, odorless carbon monoxide from the engine can get pumped directly into the cabin with that warm air. So why is this so bad? Here's the killer number: 210 times. The hemoglobin in your red blood cells, the stuff that's supposed to carry oxygen, will grab onto a carbon monoxide molecule 210 times more easily than an oxygen molecule. So the CO literally hijacks your bloodstream and suffocates you from the inside, even if there's plenty of good oxygen all around you. What makes it so incredibly dangerous is just how sneaky the symptoms are. It might just start as a dull headache or feeling a little bit dizzy, things you'd probably just ignore. But it can quickly get worse, leading to blurred vision, nausea, and if it's not caught in time, it's absolutely fatal. Okay, let's circle back to Boyle's law for a second. Remember that inverse relationship between pressure and volume? Well, it doesn't just apply to the air outside the plane, it applies to all of the gases that are trapped inside your body, too. This leads to a scary condition that pilots and divers both fear, called decompression sickness or DCS. As that outside pressure drops when you climb, the nitrogen that's normally dissolved harmlessly in your blood and tissues can start to come out of solution and form actual bubbles. It's literally the same exact principle as opening a can of soda. And these tiny little nitrogen bubbles can cause absolute chaos. If they get stuck in your joints, you get the painful bends. If they affect your lungs, it's called the chokes. They can even cause weird skin sensations that pilots call the creeps. It is a whole body problem, from head to toe. And this brings us to an absolutely critical piece of advice for anyone who scuba dives. Diving forces a ton of extra nitrogen into your body's tissues. Flying too soon after is like shaking that can of soda right before you pop the top. You are dramatically increasing your risk of getting decompression sickness. The rules are simple, and you have to follow them. The deeper you dive, the longer you must wait before you get on a plane. So it's not just about what's missing from the air, like pressure. It's also about what's in the air at those high altitudes. We're talking about stuff you just never encounter down here on the ground. You see, most of us live our whole lives down in the troposphere, the lowest layer of the atmosphere. But big jets, they fly way higher, up in the stratosphere, to get above the weather and be more efficient. The only problem is, that's also where the Earth's protective ozone layer lives. And while that layer is fantastic for blocking UV rays, the ozone gas itself is pretty toxic to breathe. And if you inhale enough of it, you can get a whole range of nasty symptoms. Everything from a hacking cough and burning eyes to headaches, and really importantly for pilots, it can actually reduce your night vision. And that brings us to our final and maybe our most important topic, because in aviation, vision isn't just one of your senses, it is the critical sense. But it's also one of the most vulnerable to all the effects of flying at altitude. Our eyes are these incredible, complex organs, but there are also total oxygen hogs. They need a constant, rich supply of oxygen to work properly. Every part of this system, from the cornea at the very front to the millions of light-sensitive rods and cones on the retina at the back, this whole thing is one of the very first parts of your body to start failing when it's under stress at altitude. And this becomes a massive deal at night. Even a tiny, unnoticeable amount of hypoxia can seriously mess up a pilot's night vision. The rods in your eyes, which do all the hard work in the dark, are super sensitive to oxygen levels. It can take them up to 30 minutes to fully adapt to darkness. In a cockpit, that's an eternity. It's exactly why pilots are trained in specific scanning techniques just to overcome their own biology. So the next time you're on a flight, cruising at 30,000 feet, just take a second to remember the incredible biological balancing act your body is performing. We've built these amazing machines that can conquer the sky, but it all still depends on that delicate and pretty vulnerable human operating system. And that really leaves us with a final thought. As we try to fly higher and faster, maybe our biggest challenge isn't engineering the machine, but truly understanding the person sitting inside it.